And Antonio is really the expert on planetary atmospheres. He has worked on both solar system atmospheres and exoplanets. So it will be a pleasure to listen to this. And I'm recording this from on my laptop now, so if you missed anything, you can go back and watch the recording from the CHEOPS webpage later. Okay, so please go ahead, Antonio.
Okay, well, thank you, Alexis, for the introduction, and thank you, everybody, for joining this webinar, and of course for the invitation to give it. So what I'm going to speak about is a paper that we recently got out, like it has been published in the Proceedings of the National Academy of Sciences. And these are the links. This is work that I did with my collaborator, Kate Isaac, at the European Space Agency. And there were other colleagues as well that were contributing in one way or another. So basically, well, exoplanet has moved really fast since the last 2 decades. And what is driving the field is, of course, finding life, which is an extremely challenging thing. And we think that if we want to find life, we need to characterize atmospheres because there may be clues of that life in the atmospheres. Of course, there will be a number of challenges in the way. There will be technical challenges, and that's why we are building new instrumentation, better facilities, etc. And there will be physical challenges, or what I call physical, which is that neither the star nor the planet want to give away their secrets. We can mention, well, if we are thinking of biosignatures, there may be false positives. Clouds will always be in the way. We already know this. And there will be no shortcuts. That's something we are coming to understand, that basically if we want to find something really interesting in the atmosphere of an exoplanet, we have to really look at all the details. So in the process, we will be learning lots of physics, which is very good, and learning about primary and secondary atmospheres. If we are sure of something, is that this effort is going to require all the tools that we have at hand, which means that we'll have to make observations with multiple facilities, using multiple techniques, and using multiple wavelength ranges. And our work is actually focusing on, well, if we go through this list of points, we are using observations from space. The technique that we are using is phase curves, and the wavelengths that we are going to probe are visible wavelengths. And so when we think of remote sensing of exoplanet atmospheres, the first consideration is what is the viewing geometry. So we can think of the planet when it is transiting, and then we will probe the planet during this time when the planet is passing in front of the star. Then if there is a secondary eclipse, we'll have like one of those on-off situations that we see the planet fully illuminated and then it goes behind. And then we will have other phases, which is where, well, the planet spends most of its time. If we think of the light that we are going to analyze during transit, we'll be seeing transmitted starlight, which is photons coming from the star that were not retained by the planetary atmosphere. During secondary eclipses and other phases, what we'll have is a combination of both. Thermal emission coming from the planet and starlight, which is reflected on the planet itself. We can ask ourselves, like, okay, all these techniques or approaches, what part of the atmosphere are they probing? And the answer to that will be, well, transmission is probing like an optical thickness of, well, really small, so we are probing the upper atmosphere. Thermal emission will be probing like, well, an optical thickness of about 1, and reflected starlight is probing deeper down. So obviously the least we can say is that these techniques or these approaches are all complementary. And this is a sketch comparing the contribution of thermal emission and reflected starlight for the hot Jupiter. So reflected starlight is dominating at the shorter wavelengths, and like for a typical hot Jupiter, we will get a contrast between the star and the planet on the order of 10 to minus 5. At thermal emissions, well, the contrast is way better, and this is why there have been, well, more efforts dedicated to look at the thermal emission, and not so many to look at the reflected starlight. The transition will be somewhere in between, like well, for hot Jupiter, it could be like at about a wavelength of 1 micron or so. And this is important to keep in mind. Planetary thermal emission. This is not the focus of my talk, of our work, but it has been very important. And with thermal emission, we can investigate, for instance, the composition of the planetary atmosphere. So we can look at the temperature profile, and this has been done. There are examples. Of course, if we see the planet at multiple phases, we can look at all these properties as the planet is evolving, and we see more or less of the illuminated disk of the planet, and this has been done as well. And all this information can be used to build very interesting maps with temperature fields that can be compared to GCM simulations. And this is the way to move forward and learn in the process. And in the case of reflected starlight, there are additional considerations. Well, this has been done. And when we see the light, which is, an optical phase curve, it's made up of a number of contributions. This is the case of Kepler 2b. You can see that the phase curve has an interesting shape, and it's because it's contributed by the planet, but there's also a Doppler and ellipsoidal contribution. So if we want to study the planet or the planet atmosphere, first we will have to get rid of the Doppler and ellipsoidal contributions. In some cases, this is naturally easier, and the Doppler and ellipsoidal contributions are negligible. That's the case, for instance, of Kepler 7b. So if we want to investigate the atmosphere, this is probably a better situation. And I will introduce, well, what is the geometrical albedo, which is an important property of atmospheres, which is that, well, assuming that the phase curve is dominated by reflected starlight, it will be what is the normalized brightness when the planet is fully illuminated, which is what I'm marking here in the sketch. There have been quite a recent, a number of works dedicated to look at the optical phase curves. It's interesting because it took longer than to do transmission spectroscopy, which is not surprising because we need higher precisions. But yeah, there has been recently quite a number of groups working on this and doing, well, looking at observational data and looking at the modeling side of all these. I'm going to focus on a very specific planet. This is Kepler 7b. Kepler 7b is quite a unique case. It's a hot Jupiter. So its mass is less than half the mass of Jupiter. The radius is about 50% larger than Jupiter. And it's one of those cases of low density, low gravity that, we don't really understand what is going on within the bulk atmosphere of the planet. And it's what makes this planet really unique is that we have data, or to me, is that we have data in the optical. So we have this was done with Kepler. But there's also, we have also information from a Spitzer, which is constraining the thermal contribution of the planet to the optical phase curve. The conclusion, and this was published by Breeze in 2000, well, there are a number of papers, 2011 and 2013, is that the thermal contribution is much smaller than the reflected starlight contribution. So that's facilitating the analysis. Kepler 7b is also special, and you can see this here. It's like, this is a plot of the geometrical albedo against the stellar irradiation, and it's an outlier. It has a really high albedo, which is comparable to the geometrical albedo of the solar system giant planets. These are the original data published by Breeze. Okay, so the goal is what can we see in this data? Well, if we beam this data, this is, I'm tracing the curve here, you can see that there is a clear trend. Like, there are 2 points that I would like to highlight from this phase curve after beaming. One is that the geometrical albedo is relatively high, as I said before, and the other is that the brightest point is not at full illumination. It will be an orbital phase of 0.5. The brightest point is slightly offset from full illumination. And that's telling us, or strongly suggesting, that the planet is not uniform. Its cover is not homogeneous. So we were looking at this data and we were asking ourselves, okay, what is the information that can be extracted from the optical phase curve? And an important clue or something quite useful is to realize that the signal from in the phase curve is dominated by reflected starlight. So that's making the analysis easier. So we thought, okay, well, we have the observational data. We can build synthetic phase curves and try to see like how well we can reproduce the observations with a physically based model producing those synthetic phase curves. And this is what we did. Basically, we set up an atmospheric toy model for Kepler 7b. The toy model is described by a number of parameters that here I refer to as P1 to Pn. We produce synthetic phase curves that we compare to experimental data. We define a quality of fitting parameter, a chi-square. We can do this a few times, and every time extracting different information about these parameters. Eventually, we will come to a combination of parameters, which is minimizing the chi-square, and then we can say that this is the best fitting solution, something along those lines. And something to keep in mind is that all the physics is contained in those, all the physics in the model is contained in the selection, in the choice of these parameters. So that's an important thing to consider. And then that the complexity of the model has to be justified. Like, well, if the model is too simple, we may be killing the problem. If it's too complex, like we can run into multiple degeneracies. And so we have to think about how to proceed with that. What we did was to set up a model, a toy model, which is made up of 6 different parameters. I will describe it then later. We are additionally assuming that the planet is tidally locked, that the atmosphere is basically, it contains a cloud on top of a gas sphere. So it's a single slab atmosphere. And the cloud is vertically uniform, so there's no stratification, but in the horizontal direction is not uniform. So the optical thickness is described with a law like this, which is 2D Gaussian, and here you can see that well, you can get an idea of that here in this sketch. There are 3 parameters describing this optical thickness. Which one is the thickness at the center of the cloud, which is tau c. The other is the offset of the center of the cloud with respect to the substellar point, and sigma, which is a width of how narrow the cloud is going to be. Another parameter, or 2 more parameters, are describing the optical properties of the cloud particles. One is the single scattering albedo, which is the probability that the photon which has a collision with a cloud particle is going to be scattered off, or it gets absorbed by the medium. So the other is the asymmetry parameter, which is easy to, this is a measure of how strongly forward or backward or isotropically how isotropic the particles are going to scatter the light. If G is close to 1, then we'll have a strong forward and backward lobe. If G is close to 0, then what we have is something close to isotropic scattering. And the last parameter in our toy model is describing what happens, how the gas sphere is contributing. And we simulate this by just a single surface reflectance. So we keep just the external surface of the sphere. So if the surface reflectance is close to 0, that means that the gas atmosphere probably, well, is strongly absorbing, probably because it contains one of these chemicals. If it's not, if the surface reflectance is close to 1, then the gas is not contributing to absorption. And we had the 6 parameters. So we built we were exploring the space of parameters according to this table. So we were building, for each combination of parameters, we were building a synthetic phase curve. In total, we have more than 1 million phase curves. And the way to produce those phase curves is to solve the multiple scattering problem. And to solve this problem, we were using a model, something that I was setting up with Frank Mills, a collaborator in Australia. And it's an algorithm that we developed ourselves, and it got published in last year. The idea of this algorithm is that basically, if we want to get the signal from the integrated signal from a whole planet, then the classical approach, what you will do is to pixelate the planet and solve the radiative transfer equation at each pixel, and then put all the solutions together. What we are doing instead is using Monte Carlo sampling, so we get the low accuracy solutions here and there, but then when we put them together, we get basically high accuracy solution for the whole disk. What I can say is that this Monte Carlo approach is clearly outpacing the other pixelated approach. So this is good when you have to produce more than 1 million synthetic phase cubes. And the chi-square quality of fitting parameter that we define is obviously depends on the 6 parameters in the toy model. So we were checking what is the contribution of from each parameter separately. And this is a brief summary of what we found. I'll be describing some of these details later. So what I like to just general remarks. One is that if we are comparing phase curves, we will have information which is coming from, say, the peak of the curve, something that we will get also if we do secondary eclipse measurements or the simulation of secondary eclipses. But with phase curves, we have additional information coming from not only from the peak of the curve, but also from the shape of the curve. So in a way, we are increasing the dimensionality of the data that we can compare to. This is something that we cannot do with secondary eclipses, where we will have only a single value, like not the shape of the curve. So I'm going to explore what is the effect of the parameters in the toy model. This is the optical thickness at the center of the cloud. And basically what happens is that, if we run simulations for a number of optical thicknesses, typically what we find is that the signal or the brightness of the planet is increasing when the cloud becomes thicker. And so we can think backwards and then go back to the case of Kepler 7b. And as I said before, the geometrical albedo is relatively high. So this is probably already suggesting that for Kepler 7b, we will need a cloud which is optically thick, probably. And let's go to the second parameter, which is the cloud width. And this is running a simulation with all the parameters frozen, but the cloud width. And what we find is that, if the cloud becomes very wide, say that we get to this pink case, and even if the cloud is offset with respect to the optical, with respect to the substellar point, what we are going to get is that if the cloud is becoming wider and wider, this offset becomes less and less important, and the curve becomes symmetric with respect to the full illumination geometry, which is optical orbital phase of 0.5. So again, going back to the case of Kepler 7b, we saw that there was an offset in the curve. So this is strongly suggesting that the cloud has to be wide, but not too wide. So this is something to keep in mind. The next parameter is the shift or the offset of the cloud with respect to the substellar point. So this is a number of simulations where the cloud is more and more shifted with respect to the substellar point. And what we get is that as the offset increases, the point at which the phase curve is peaking is moving towards larger values of the orbital phase. So again, if in the case of Kepler 7b, the peak is occurring in this region, so this is already constraining that, we will have an offset in the cloud position, but it cannot be too small, and it cannot be too large. Okay, the next parameter, is the single scattering albedo of the cloud particles. This is important because this is connecting us to the composition of those cloud particles. And the synthetic phase curves are extremely sensitive to this parameter, as you can see here in this plot. Basically, like if the cloud particles are fully conservative, we will get the black curve. But just a small decrease to, well, relatively small to 0.9, basically it means that the planet becomes 3 times dimmer. So really this parameter has a strong impact. And well, this has to, the reflected contribution, like it scales in a way like this, like it's a summation of powers of this single scattering albedo. So how rapidly we can sum this contribution will depend on how close we are to 1. And again, going back to Kepler 7b, we saw that the planet is highly reflected. So this is strongly suggesting that, well, we will have a single scattering albedo relatively high. Okay, next parameter is the symmetry, the symmetry parameter of the scattering phase function of the particles. And the scattering, well, in this sketch that I'm showing here, this is what will happen. I mean, this is the way that particles will scatter light if the G value is close to 1. There will be a strong forward lobe and a strong backward lobe. And when G is close to 0, this will be like almost isotropic or isotropic. And what is the impact on the phase curves of the planet? Well, you can see this here in the simulations that I ran. When G is small, like the curve is really smooth. When G is getting closer to 1, what we see is that the shape is really changing, and it becomes sharp and peaky here at close to full illumination when we have a geometry of a backward scattering. Going back to Kepler 7b, what we have is that we don't see much structure, not even like close to full illumination, close to secondary eclipses. So this is strongly suggesting that the G values will be either small or moderate. So we are, step by step, we are building our cases of what we should expect. In our paper, we were considering 2 different treatments for the scattering by particles. One was the double, we were considering a parameterization which is called double Hange-Greenstein. This is convenient, it's a simplified parameterization. But anyway, we were later confirming our results with mean scattering, which is much more physically based. And the good thing about mean scattering is that it is giving us, with the double Hange-Greenstein, we can get an idea of the G value. With me, we can go even farther. We can constrain the particle size of the clouds, of the clouds. And these are simulations when we use, like in this panel, these are the simulations when we use the double Hange-Greenstein formulation, and this is when we use mean scattering. So the general trend is that, yes, when the particles are larger, the G value increases and the phase curve becomes pointy in the geometry of a full illumination, like close to secondary eclipses. And the last parameter to explore is the surface reflectance. And this is a number of simulations that we were running with different values of the surface reflectance. And what you can see is that the effect is weak where the cloud is thick, but the effect is strong when we are probing the wings of the cloud, because then the photons can get through to the surface of the atmosphere. And you can see that if the cloud is, if the gas is very dark, if the gas sphere is dark, the wings are the wings of the phase curve go to 0 relatively quickly. However, if the gas sphere is not so dark, what we will get is a significant contribution at optical at these orbital phases. And going back to Kepler, well, I can tell you that in the case of Kepler 7b, the data here go relatively quickly to zero. So this is already suggesting that the values consistent with the Kepler 7b data will be those that are associated with the small values of the surface reflectance. And the chi-square is, as I said before, is a function of the 6 parameters. Well, we don't have visualization capacities in 6 parameters. So what we were doing was to look at this chi-square function, comparing one parameter to another parameter. So basically reducing the dimensionality from 6 to 2 and going through all the different parameters. And we obtain sensitivity maps like this, where each map is corresponds to the 2 different parameters. Like for this panel of chi-square 2-dimensional maps, well, this panel is specific to a surface reflectance of 0. And this is what we get when the surface reflectance is 0.1, 0.2, 0.3. Now I go back to the beginning. Like the dark regions are where we have relatively good fits to the observational data. And here in this plot, what I'm showing is the minimum chi-square for each of those configurations where the surface reflectance is 0, 0.1, 0.2, and 0.3. So what we see is that for surface reflectance of 0.0, we have a chi-square like this. For 0.1, it's less, and then for 0.2 and 0.3, the minimum chi-square is increasing. This is already telling us that we are getting better fits to the data when the surface reflectance is relatively small, and this is something that we can directly compare to photochemical models of exoplanet atmospheres. I'm going to present now the observational data, the data after binning. This is the pink curve, and then all this, what I'm tracing here with my pointer is a bunch of lines of synthetic curves. All of them, well, there are 6 of them, and they correspond to very different configurations in the toy model of the atmosphere. So in a way, of course, all the synthetic lines are indistinguishable from each other. What I'm saying is that we can have multiple combinations of the model parameters and get relatively good chi-square values. So in a way, what is clear is that the problem is degenerate. So now we can ask ourselves, okay, well, there are degeneracies. Should we stop there? And the answer is no. Well, because we can, even if there are degeneracies, we can still constrain a few important parameters. And let's look at that. This is a few plots coming from the panels that I was showing before. Like in the vertical, we have the optical thickness at the center of the cloud for each of these plots. And what we see is that the best fits happen when we have an optical thickness at the center of the cloud of about 50. So the first conclusion that we draw is that we need an optically thick cloud, at least at its center. Maybe at the wings it cannot be so thick, but at the center the cloud must be thick. And then we can look at what happens with these 2 parameters, the width of the cloud and the offset with respect to the substellar point. And what we see is that the region of good fits is this one, and it's quite elongated, it's quite extended. So basically there is a sigma there's compensation between the 2 parameters. And so this is telling us that we could find good solutions with a cloud which is say at a position like this and this width, or with the cloud which is more offset with respect to the substellar point, but it is wider. So because in both cases we will get optical thickness over the rest of the planet, which are equivalent. And looking at another specific case about model degeneracies, this is, well, in the vertical direction, what we have is the single scattering albedo. And it is clear that good solutions or good fits are provided only in the cases that the single scattering albedo is close to 1. And we were putting a limit of 0.99, and this is quite important, actually. And yeah, so the next parameter to look at is what happens with the asymmetry parameter. The symmetry the symmetry parameter is a measure of how isotropically the cloud particles are scattering light. And what we see is that good fits are obtained over a range of values of these two parameters. And typically the good fits are obtained for G less than 0.7 or so. Like for larger than 0.7, what we get is a structure close to secondary eclipse that we don't see in the observational data. Yeah, so far we have been constraining, putting constraints on these 6 parameters. And what I'm trying to convey now is that if we have some additional information, like for instance, information on the temperature of the planet and on the condensation temperatures of plausible condensates, then we can obtain or put limits to 2 additional parameters. One is the refractive index of the cloud particles, and the other is the particle size of the clouds. And so basically, we are moving from the single scattering albedo and the symmetry parameter to 2 parameters which are more physically based. And this is interesting, particularly in the case of the refractive index, because then there is a direct connection to composition. This is a table that in a paper that was published by Wakeford and Singh in 2015, this year, yeah. So there is a list of condensates with condensation temperatures. We can first consider what is the equilibrium temperature of Kepler 7b, because this is probably this is giving us an idea of the range of temperatures that we should expect in the atmosphere. The equilibrium temperature is about this 1600 Kelvin. So it is fair to remove all the condensates that have the condensation temperature which is less than 1000. Then we can look at an additional condition, which is the single scattering albedo, and see which ones of these plausible condensates has a single scattering albedo which is larger than 0.99, which is what we were able to constrain before. And there are not so many, actually. Like we have silica, we have perovskite, we have 2 iron poor silicates. And in all the cases, the imaginary part of the refractive index is less than 0.003, so that's really small. In the other cases, the condensates are they absorb strongly, so the single scattering albedo will be less than this. Next, we want to go from, we want to infer or see how we can go from the single scattering albedo and the asymmetry parameter and try to retrieve the particle size. Once we have like 3, at least, we have 3 plausible condensates, and we know the refractive index, the refractive indices for all of them. So this is the way to do it. Like we can plot diagrams where we represent the single scattering albedo against the wavelength, or against the particle size, or the effective particle size, which is the ratio of the particle size and the wavelength. And typically for like a silicate, it will be like this curve will be something like this. If we put the constraint of, okay, the single scattering albedo must be larger than 0.99, this is bracketing the range of particle size that are consistent with our constraints. We can do something similar for the asymmetry parameter. In the case of the asymmetry parameter, what we found is that this parameter must be less than 0.7. So this is also constraining how large the particles can be. And the conclusions that we drew is that particle sizes, the actual range depends if we consider silicates, perovskite, or silica, but it should be in the range of 0.1 or 0.4. So there will be small particle sizes. So this is a brief summary of the retrieval of parameters. And I'm not going into the details so much. We managed to put constraints on the surface reflectance or how absorbing, how dark the gas atmosphere is going to be. What is the range of particle sizes consistent with our observations, and how absorbing those particles can be. If I want you to take away a few ideas, it will be these ones. First, that with our modeling, we came to the conclusion that we need a cloud, and the cloud must be offset with respect to the substellar point. And another conclusion is that we need clouds which are conservative, like they don't absorb much, and that the particle sizes of those clouds must be small. Otherwise, we'll see a structure which is not present in the observations. And well, in the process of analysis, we were asking ourselves, okay, there are degeneracies. Is there anything we can do to do this better? Like, how can we overcome these degeneracies? And do the degeneracies depend on the signal-to-noise ratio? So what we did was to set up a thought experiment where we were taking the best fitting synthetic curve. We were adding a white noise at the 20 ppm level, and then we were doing the extraction exercise, and we were constraining properties like this way, what I'm highlighting now. Okay, what if we do the same experiment and with white, by adding all like white uncertainties which are less than 20 ppm, let's say only 5 ppm, let's forget whether this is technically feasible or not, but let's do it. So we were doing it, like we did the extraction exercise again. And well, we come to the conclusion that the degeneracies are still there. Like we cannot, even if we have much better data, the extraction exercises still degenerate. So basically, there were two important conclusions: is that once you have reached a given signal-to-noise ratio, getting better than that doesn't mean you will be able to constrain the properties of the atmospheric model better. And the second conclusion is that this degeneracy is intrinsic to the interpretation of photometric curves. It's something that doesn't, it can get worse if the signal-to-noise ratio is bad, but if it's very good, there's a limit that you cannot do better than that. We were also thinking about what if we had the observations at multiple wavelengths. Like some of this, we know that some of these parameters in the atmospheric model are strongly dependent on wavelength. And so maybe this is a way to get additional constraint. This is a simulation for Kepler 7b. The 3 different wavelengths. So what we can see is that clearly if we were observing the planet with different color filters, we will get different phase curve shapes. So this is not the full proof, but my guess is that yes, if we had multiple wavelength observations, we'll be able to improve the constraining of the problem. Well, if we really wanted to do this better, probably what we will have to do is to do polarimetry. We have known this for decades from the specific case of Venus. And well, the reason is that when we do photometry, the phase curve in photometry, and this is the phase curve of Venus, doesn't contain much structure. Basically, the curve is quite monotonical. If we do the same with polarization, what you can see is that the phase curve contains quite some structure, and this structure is very useful to constrain some of those properties that we put into our model. This is well, a few simulations that I was running for Kepler 7b. This is what we will get in brightness in photometry. So this is like, okay, we are getting data. Well, I mean, we have facilities which are making this type of observations, and the 3 different curves correspond to 3 different cloud particle sizes. This is what we will get if we were doing if we were observing the planet in polarization. So what you can see is that well, small changes, or well, significant changes in the particle size, like, can change moderately the shape of the brightness phase curves, but they change radically the polarimetry phase curves. This is something that we are not going to do for quite some time, so that's why I refer to it as daydreaming, but it's something, well, just to keep in mind. Maybe one day we'll be able to do what we are doing now with in a space with photometry, but not only observing the intensity, but also the other elements of the Stokes vector. Yeah, something to do in the future. Now I would like to emphasize a few implications of the work. And one of them is what can we say about the clouds and how high they form. So the story goes that as we increase the temperature of these hot Jupiters, like, the clouds are disappearing, unless the gravity of the planet is really low, in which case, like, we can, well, small particles can get high up in the atmosphere and stay there. Actually, Kepler 7b is one of those cases, and so we may be in one of those situations that was described as class 5 by Sudarsky and collaborators in 2000. And of course, if we are going to put clouds high up, we have to, well, there will be constraints about at what altitude we can have those clouds. We can see that sodium is strongly absorbing in the visible. So if we want to get rid of absorption from sodium, probably we will need to put the cloud really high up, so sodium has ionized, according to recent photochemical models. So you see, we can already connect some of these parameters that we were inferring to photochemical simulations. General circulation models, well, of course, they are giving very important clues to the interpretation of this type of observations, like starting by, well, they allow us to constrain the type of cloud geometry that we may have, whether it's forming on the east or west hemispheres. It's producing temperature fields that, well, they are telling us, okay, when we are going to reach condensation temperatures, and when and where. And they are telling us also, okay, how strong winds are mixing those particles, and this is critical to keep the particles high up. And ultimately, like, okay, general circulation models are including both, well, they are including phenomena like microphysics and also photochemistry, so they will be extremely important to do the interpretation of these models. Additional implications, well, I was what I said is that the observations of Kepler 7b are consistent with submicron particles, and the particle size is critical when we are doing transmission spectroscopy, because well, the shape of the Rayleigh slope is strongly dependent on this particle size. So basically, in the case of Kepler 7b, like, we will have a particle size something like this. What I will expect is that it will have a Rayleigh slope, and this is something that maybe can be tested in the future. Maybe if not with Kepler 7b, maybe with a similar planet orbiting a brighter star. An additional, well, something, or I guess, is that, well, okay, if the cloud is not symmetric with respect to the substellar point, if we manage to do transmission spectroscopy of one terminator or of the other terminator, we will probably get different results. Again, this is something that can be tested, hopefully, in the future. I do theory, but of course I'm aware of the difficulties of real observations. So I'm going to mention potential killers to this type of a study. The precisions that we need are really high, And we know from transmission spectroscopy, we have been learning this over the recent years, that there are stellar effects and instrumental systematics that may interfere with the interpretation of our observations. Well, photon noise is not necessarily an issue if we pick a really bright star, and this is probably a focus of CHEOPS, but stellar activity is something there's no easy way to deal with. So I guess the focus should be to look at the quiet stars to avoid issues related with the stellar activity. The way to do this, well, probably we will need to understand better the stars and make observations on multiple wavelengths. We will have to incorporate the lessons that have been learned from radial velocity surveys. And something really important that I consider, which is very important, is that we will have to duplicate observations. So look at the same target a number of times and look at the same target with different facilities over and over. So we can be sure that systematics are not affecting the interpretation. And also keep in mind that the planets are not static. Planets are variable. Planets are variable. And I like to show this example of Venus, where overnight we can see increases in the brightness over areas of 1,000 kilometers or so, like increases by a factor of 30%. And this is for Venus, and we don't know what is causing these increases in brightness. So I guess we have to be open-minded. The study of optical phase curves has been, is really active. Like I was mentioning, I was referring to all these applications, but there are many more, and then I'm listing here. And this is reflected in the number of recent publications addressing the investigation of the optical phase curves. I'm still working on, I'm working on this. This is a major emphasis of my current work. I'm planning to extend what we were doing for Kepler 7b to other planets, and probably to set up a more robust framework to do the interpretation and focus on the regions close to secondary eclipse. I think this may be more suitable for data coming from missions like CHEOPS. I think CHEOPS can contribute significantly to all these studies. Particularly its focus on bright targets. That's really key for follow-up studies with other missions or ground-based telescopes. Again, I would like to emphasize that duplication is very important. Like CHEOPS should look at planets that for which there are already observations, and again, like future missions should look at planets that for which CHEOPS was obtaining data. And this way we will get eventually data both in the optical and in the infrared. And I think CHEOPS should look at both transiting and non-transiting objects and try to understand differences. This is my last slide, and so it's going to be really simple. I think, I hope that I was conveying that optical phase curves contain important or atmospheric information, and this is a characterization exercise that we can do now. We have the data. Phase curves are very complementary to transmission and thermal emission. We will need all of them and any other remote sensing techniques that we can figure out. This type of studies, so far it has been done with COROT and CHEOPS, also with MOST, and in the future we have a number of facilities that can really push this forward. And all these exercises are putting us on the right track to, eventually we will get phase curves obtained by direct imaging missions, and I'm thinking of WFIRST. So doing all these exercises is a good preparation work. And finally, I would like to emphasize that, we are combining the work of astronomers and atmospheric sciences. This is something that requires input from those two communities, and it's important that the work is done jointly. So I think I'm done now, and thank you very much.
Thanks a lot, Antonio. So we have some time for questions now, if there are any questions. then please go ahead and ask them.
Hi, Antonio. This is Don Polacco.
Hi.
I just have a quick. Could you put your last slide back up again? Your conclusion slide at the end. It's just. I often see these slides, and I wonder if people have really thought about them. So you've said there, for instance, that this is important for directly imaged planets, like when W first comes along.
Yeah, can you see the slide now?
No.
No, I can't.
No, okay, sorry.
It doesn't matter. It doesn't matter. We can talk about it.
I will put it back.
And I just wonder, have you actually done the calculation to know that the planets that W first will see?
Yeah, well, I haven't done it myself, but there was recently a paper out on AstroPH, and like they were aiming for a contrast on the order of 10 to minus 9. So that's enough to look at the Jupiter-like
But what
planet.
orbits? I mean, are these orbits that are you know, Jupiter and bigger?
Yeah, Jupiter and bigger. I mean, what I mean is that we will be looking at the different family of planets. What I'm saying is that the ideas from the theoretical perspective are similar. Like, like W first will be looking at cold Jupiters, and here we are looking at hot Jupiters. So the orbital distances are very different, but this is a good preparation exercise to the characterization.
Yeah, I understand that. I just want to know whether or not we can do this when W first comes. You know, you see what I mean?
Well, if they get to accuracies on the order of 10 to minus 9, we should be able to do it. Yeah.
And have you looked at phase curves with TESS?
Well, not really. I was asking actually, and people were kind of skeptical because this is
10 centimeter apertures.
Yeah, exactly. So that's a big thing. I was also paying attention to the systematics that they expect, although this is something that can change, of course.
Yeah.
And they were aiming for systematics on the order of 80 ppm, if I recall correctly. So this may be an issue as well, but I'm pretty sure that people will be trying to look at this.
I'm sure they will. I'm sure there's no accident that it's 80 ppm either. That's the Earth size detection. So that's what they're aiming at. But anyway, very interesting. Very, very interesting, in fact.
Okay, thank you.
Thank you. Are there any more questions? If so, just unmute your microphone and ask the question. Lee? Yeah. Okay. So if there are no more questions, I'd like to thank Antonio again for agreeing to give this very interesting webinar. And as I said, we will be posting it on the CHEOPS website, so you can watch it all again if you want. So thank you all.
Okay, well, thank you all. Thank you very much.
Thank you.
Thanks a lot. Bye-bye.